Shelby, what is this?
Listen, I heard that I could bring in props for this episode.
We got props.
We
just finished an interview. What this be?
These are those things you find in every shoe you order, or
right.
jerky bag.
That's right. You
pack of jerky.
Right.
They always have these little. I mean, this is normally what they're
right.
like tiny, but I found some big ones just for scale.
Why?
But they're relevant today.
Okay.
We're talking to dynamic duo Brent Staley and Spencer Oulman.
Right.
I almost said got their last name
right.
swapped because they're always together. You know, they're great to talk to together. And we're talking about gas dehydration.
Right.
Which is what
hence the
kind of these do.
Little silica packs. Yeah.
Get the humidity out of the air.
Right. So it's a good visual for us to understand the complex nature of what they were talking about. We just went through it, and there are some difficult things to understand, but then eventually, they distilled it down to a really simple message.
They dehydrated it down.
They dehydrated it, the message down to below 50 parts per million.
Right.
And at the end, I was like, oh,
yeah,
it's actually quite simple to understand, but to get there took a very complex process.
Right. And I know a lot of times our episodes are shorter, and so I want to invite the audience to hang on. This is almost like an educational episode. I feel like we really go through the background of how this works, and then into what, spoiler alert, smart bed is the technology. We're kind of at the end talking about what it does and how it works. But to get there, we had to give some background.
Right.
So there's a lot of really interesting, I think, if you're in the carbon capture space, or if you're in the space of needing to, of already knowing what these things are, temperature, let's say they're all different keywords.
Yeah.
Or if you're not at all and you're just curious about different parts of the industry you may not have ever heard of, I think it's a really interesting episode.
I think so. So pop your popcorn, get out your beef jerky, take your silica packet out of there, don't eat it, and enjoy the show.
Enjoy. Welcome to the studio.
Thank you.
That's right. Brent, Spencer. Glad to have you.
I think we had y'all in the old studio, maybe.
We did.
We did.
Minnesota.
Yep.
And we've done some video stuff with y'all separately as well. So I feel like we have a long partnership that we've been doing things together. This is like the next iteration.
Always a pleasure.
Of you guys with us. So yeah.
Thanks for having us back.
Yeah. What are we talking? Gas dehydration. What are we talking about? Can y'all give us a little introduction about what it is?
Sure. So for any gas that you have, whether it's a product or it's a waste stream, unfortunately, it's not in fit for purpose condition. So you have to do something with that gas to make it to meet the specifications for sales gas or for the waste stream.
Okay.
And in almost all applications and almost all gases, that requires gas dehydration.
Okay. I was thinking, it makes me think like mining. Like when you go and you mine for ore or something, it's not like Minecraft and you can pick out, oh, here's my gold and it's perfectly good to go. All the elements are mixed together. Cobalt is mixed with nickel in the same way. Is it kind of the similar, like there's different elements inside this gas that you need to get out to make it something usable?
It's similar in the sense that where the gas is coming from. So in the case of natural gas, when it's coming out of the ground, it's been sitting there in formation with a whole bunch of other things. So it's not just CH4, and that's the only thing in that natural gas. There's all sorts of C2 to C8 different components in there.
Yeah, I was going to say C2, C8, C7, C11.
Meth, eth, prop, any of the anes, enes,
220,
other
221.
stuff that's in there.
Yeah.
So all those materials come out with it, as well as hydrogen, carbon monoxide, carbon dioxide.
Right.
And it's all saturated with water at the temperatures they're in as well. And it's also at pressure and temperature. So essentially is what comes out is whatever was down there, and then you got to get ready for transport as well as a use as well. In similar sense for hydrogen and CO2 is it depends on where it's coming from, what's happening upstream. All those things tie back into the actual condition of the input. It is not in the state that Brent said is it needs to be. It's low moisture for many reasons.
Not a simple operation, it sounds like.
Depends on a lot of factors, basically. Yeah.
And moisture in any gas is not good for when you transport that gas or when you store it, because it can cause corrosion and other host of issues.
Yeah.
Okay.
Well, on those issues, so what I guess is the challenge that customers are facing in gas dehydration?
Yeah, kind of the big challenge is and we're going to talk a couple different gases, CO2, hydrogen, and natural gas or methane primarily. And they're all in various different aspects of what the challenges may be. But generally speaking, corrosion is the number one issue. And that's because you're going to take the gas from point A and get it to point B. In the case of natural gas, you're eventually trying to get it to users, or whether it's a chemical plant or an actual user for a stove, that gas needs to be in a good condition for the whole journey along the way, but also in the conditions that it actually gets used by the end user. For hydrogen, typically most of the projects we're talking about right now for dehydration basis are on green hydrogen. That's coming from electrolyzers. So the power goes into electrolyzers, water gets formed into hydrogen and oxygen on separate sides, and then the hydrogen is also laden with water that comes out. And the specifications there are based around the use, and it's typically for power storage. It can be put back into a reverse electrolyzer or a power fuel cell in that case, and it needs to be low moisture for the input there. And then on the CO2 side, most of the predominant projects are looking at transport of CO2 for a point source emitter, and then all the way into the ground for long-term storage. And that gets back into the corrosion side. Another side is on the hydrates, which is kind of an interesting formation of material, but it's kind of a pocket held together by other components. So in the case of hydrates and natural gas, it's not ice, it's not a crystalline structure, but it's this kind of semi-amorphous, which becomes really problematic because it'll basically plug up your entire system. So that aspect, and then there's compression, transportation issues, so a whole host of other things. But kind of the two big ones is it's all around being able to flow the gas through a pipeline or through a system as well.
Okay.
And so then on the flip side, we have those challenges. What are solutions to this? How are they currently, or how do we kind of address those?
So for CO2 or for methane, there's technologies that exist for removing the water for dehydration to different levels. And there's a few different technologies that are in our portfolio that do that. The first one is glycol, and temperature swing absorption technologies is another technologies that we have kind of at our disposal. Spencer, you want to walk us through what kind of each of those technologies look like and how they work?
Sure, and Brent mentioned glycol. Typically for methane dehydration, it's triethylene glycol or TEG. It's an absorption process, meaning that the moisture is basically taken out of the gas stream into a liquid solvent or a liquid material like a glycol. And what that's doing is basically gas comes up, liquid comes down in a contactor column, and it allows the transfer of that moisture from the gas stream into a very hygroscopic, basically meaning that the liquid loves water, so it just pulls it straight out of the atmosphere. And then the TSA, or the temperature swing absorption, is more of an adsorbent. So that is similar to what you brought here, these
I was going to say, I brought
We
some
all know
props.
these things.
desiccant pox, and it's essentially a structure that has pore sizes that, as the gas and the different stages as well as the moisture comes through, it allows for different size molecules to get embedded in there. And it's just a different technology, but you mentioned temperature swing absorption. That's kind of the primary one that we're looking at for most of the applications on the main gases we're looking at. But there's also pressure swing absorption, but it's the same principle. Is you're basically taking a gas stream with high moisture contents, and then you're basically regenerating it afterwards as well. I think we'll show some pictures later on that you basically have kind of a multi-bed system. So in this case, it's basically picking it up, and then when it's done, you throw it away.
Right.
Well, in a large-scale gas plant, you don't want to be throwing away several hundred tons of media every single time. So
They have just thousands of these. They just
just
rip
put them in and
open,
take them out.
empty.
It's the most expensive process you'll ever run. No,
Yeah.
in reality, what's taking place is you have a bed A with the stuff in there, you have a bed B with the media in there, and what's happening is you have one bed that's in adsorption mode, or taking the moisture out of the gas, and you have another bed that's in desorption mode, which is basically releasing the moisture from the media.
Yeah.
So it's constantly switching back and forth, hence the temperature swing adsorption.
Okay, we were talking about this before. It is getting technical. That is very technical. What I'm thinking though is like, what's our unique take as NOV, just on the process in general? Have we been doing this a long time, or is this relatively new step for NOV into this, or
For the industry. I
Or-
don't know.
yeah,
Like, is it new? Like,
yeah?
I'd say it's more of a translation into new industries, new markets
Okay.
in the last several years. But as far as dehydration technology, no, it's not new. This is 50-plus-year-old technology. We've been applying it towards onshore and offshore applications for gas processing, both in the TEG side as well as the temperature swing absorption side But there are some new technologies coming in as
Right.
well. And, we mentioned TEG. Well, there are other glycols. There are other solvents that can be used for dehydration.
Cool.
Likewise, there's always advancements in the media. Typically, when people think about TSA, they think of emulsive. Most people in the gas processing industry
There we go.
I was like,
think of
that's not the
emulsive
acronym.
as the first application for TSA.
You had me
Correction.
pegged.
Yeah,
I was
like-
thinking
I was
emulsive.
like, the acronym for TSA.
But there's a lot of other medias out there as well.
Okay.
So there's alumina silicates, there's activated alumina, there's 3A, 4A as far as the pore sizes on what's
Right.
going in there. So there's a lot of complexities that go into it. And it's really not that there's a new application technology, but it's really applying the right technology towards the gas stream and the expectations. And some of the new things coming out are the regulations and the expectations of those gas streams and the offtake requirements are changing. And I think we'll talk about that as far as some of the regulation and another question here as well. So,
One thing to point out is there are crucial differences between the technologies that have implications to the economics or the energy that's used in the process. And there's advantages and disadvantages. And one way to make it a bit more basic in the conversation is glycol or TEG is a technology that is the most economic or the cheapest solution of the technologies. The temperature swing absorption technologies are more expensive, more energy intensive, but they get the water content down to a much tighter,
Right.
lower water content spec than the glycol. So it depends on the applications that you use. You want to use the technology that's best fit for and most suitable for
Right.
that application. Where NOV comes in is we have the experience of the last 50 years
Yeah.
of using these technologies in the oil and gas industry that we can really help guide the direction of what technology selection
Right.
and get the best technology suited for that application.
Right. That makes a ton of sense.
Yeah. And I did want to mention, so what we were holding up, viewers, or if they're listening, these are like the little things we find in every, shoebox, jerky
Pretty much
package.
any beef jerky, but like any electronics, I think comes
yeah,
with
they
some
kind
of
of
that
have
in
these.
there.
We have different, we got some
Yeah.
big ones, but, and that's kind of what y'all are talking about is these are made to keep keep moisture out of those spaces where we don't want it. And that's kind of what we're talking about is taking what's in the air and
it's got a
separating it.
box with a certain amount of humidity in there, and this is just basically lowering the humidity so you're not going to have condensation and,
Right.
and water droplets forming in your box when you pack it and ship it from point A to point B.
Yeah.
Simply.
Can you explain? I know you kind of touched on it, but so that's in this form. So when y'all are using this kind of similar technology, but very different, can you re-explain a little bit on, I guess, how these relate to it a little more?
Well, if I rip this open, I'm not because it's going to make a big mess, but you'd see these little granules of media. They're basically just these structures. If you look at them in a microscope, you're going to see very small fissures and depth that's within those. And it's selectively taking the molecular size of moisture or other gases, because there's other uses for these type of media. But in the case of dehydration, it's basically allowing moisture to get embedded in, and it doesn't like the other ones because they're too big. So very, very crudely, you could think of it almost like a sieve or a filter. It's allowing certain things to come through and get embedded in, and it gets held in there, and it doesn't let some of the bigger ones to go in there.
Right.
Or it allows super small ones just to pass right through as well.
Right. Thank you for doing that. I was like, I know we had these. I wanted to make sure the audience was
Yeah,
like,
yeah.
why we had
It's a
them.
good visual,
Yeah.
so it's good to just make sure we know what we're talking about.
Appreciate it. So in those different various solutions, what are some challenges even in those that we face that we're addressing kind of now?
Yeah, well, it depends on the application. Like I said, each application has its own set of requirements or specifications to prevent the downstream corrosion in the infrastructure. And like for natural gas or methane, for many, many, many years, we have a set of standards for removing the appropriate amount of water, so you don't see water drop out in your compression stages or in the pipeline to cause corrosion. For a gas like CO2. In the U.S., we've been handling CO2 in pipelines that are dedicated for CO2 for 50 years for the enhanced oil recovery industry. And so the best practices and standards for dehydrating and conditioning CO2, relatively well known.
Yeah.
But in carbon capture, as this industry is developing, you're now taking CO2, whereas in the natural gas industry, the CO2 coming from that industry and used for enhanced oil recovery is relatively well known, has very few It's the impurities are relatively low,
Right.
which impurities complicate water. So when you have more impurities present, then corrosion can happen at a lower water content level. So now that you're introducing CO2 from a variety of point sources that have different impurities, you're going to have to remove more water so that the corrosion potentially doesn't happen
Right.
downstream. And so now there's the governing body in the U.S. is PHMSA for regulating CO2 pipelines. And they recently put out a notice proposal that says the water content level has to be at 50 parts per million. Whereas before, typical oil and gas industry for enhanced oil recovery was 600.
Oh, wow.
So it's quite a bit more strict
Right.
in terms of the water content level you've got to get to.
And you're saying that's because of like kind of just the impurity of the water now is so much higher that you need less water proportionally in the gas stream.
There's a bit more to it. Is that
Okay.
when you're dealing with methane, methane and water doesn't form an acid.
Okay.
When you're dealing with CO2 and water does form an
Right.
acid. So carbonic acid is naturally formed in the presence of free water. So in that case, you're just naturally, it's not even impurity, it's the main gas stream at that point.
Sure.
When you're talking about methane, trace amounts of CO and CO2, then there are opportunities for the acid gas formation, but it's at a much larger scale when you're dealing with CO2 because any bit of CO2 that goes into the water, there's more ready to go. So when the water forms scale and rust and corrosion products on the steel, which is typically for the pipelines, it's constantly refreshing that acidic formation, so it keeps processing it. So it's really, really important to not have free water. It's really important to make sure that you don't have free water between the point of injection and the final destination as well.
Right.
And you've got environmental aspects, you've got cooling. So any point along that is you've got gas, you have saturated gas streams with moisture, you're going to have the opportunity to form free water and continually form more acids in there as well. So it's a process. There's a lot more to it than just one or the other. And impurities is there's a lot of complexities into different gas streams. And then talking about impurities is whether it's SOx or NOx or other elemental sulfur aspects. Now you're talking about a cocktail of acidic formations that could come in there as well.
And at those lower, for example, 50 parts per million, the lower water content levels, the technologies that we've been using for 50 years in the oil and gas industry, TEG or glycol, they can't achieve lower than that. And so now a lot of these projects are having to shift to other technologies that are a bit more advanced and a bit more energy intensive with higher capital costs, higher operating cost, which is challenging with regard to the CO2 industry because it's a waste stream, so it's cost prohibitive.
Right. But is that then, I guess, since we're here now, forcing innovation forward? Like it's making things harder to do. You're talking about things are more difficult because the regulations are more stringent. But I would imagine maybe the upside of that is it's pushing, companies like NOV to innovate and be like, okay, here's a new solution or here's a new combination of existing things that haven't existed before.
Definitely. And it's almost been an education journey as well as new technology journey. And I'd say more like 90% education, 10% innovation. Just in the sense that like many of the adsorbents or the TSA processes, those aren't new either.
Right.
It's just they've not been traditionally used in the applications that would be typical for the pipeline industries and things like that.
Right.
And it's kind of like TEG is the workhorse of the industry, still is. But as you start getting from 600 to 100, 100 to 50, well, if your spec is 50, that means you're actually trying to manage something less than 50. So you're talking 20, 30 ppm for most applications to make sure you never go above that specification.
Right. There's probably usually a safety factor involved in any type of engineering spec that you would be designing toward.
Correct.
Yeah.
So it's kind of, education is more like, today, I don't know what percentage of Texans drive F-150s, but it's like, the mentality in Texas is, I got to have an F-150. Well, why? Well, I need to go pick my kids up. Well, you can do that in a Honda Civic. Well, but I also need to pull my boat once a year. It's like, okay, there may be applications where it does make sense, but in most cases, to get groceries to pick up kids is like a small small sedan is probably perfectly fine. And this is kind of that same way as like, if you're just wanting a TEG unit, we'll help you with a TEG unit. But the reality is as you start getting tighter and tighter, it becomes more and more complex as far as stripping gases and sizes and the overall flow rates of TEG. Now all of a sudden your costs become actually more advantageous to shift towards something else.
Yeah.
So the education process is really looking at the opportunity, the requirements, the offtake expectations, and fitting it for the purpose rather than just a classic out of the box. This is what you need.
Right.
So
So these challenges y'all are discussing do they change depending on the gas you're working with, or what are the kind of differences there?
yes, I would say it changes on the gases, but it also changes on the requirements. So it's not an easy which one's best type of scenario. If you look at the main technologies that we're packaging today for commercial opportunities, is you kind of have TEG on the high moisture range. So if you're operating in the 50 to 100 to 600 ppm, TEG's a great solution. It's a workhorse out there in the industry, and it's well known and it's well established. When you start getting into below 100, questions start coming up. And does it still make sense? When you get down below about 50 ppm, that's where you start getting into the TEG's not really your go-to anymore. And then you get into 30, 20, 10 ppm, and that's where that BSF Zorbede or aluminosilicate material starts to come in. But there's some trade-offs, right? Is that if you're trying to do a low moisture specification with TEG, you're actually going to kind of go opposite on the curve from a cost standpoint. So that's where it kind of bridges into that next zone of more the BSF Zorbede. Your capital costs do increase. The availability for waste heat kind of dictates your operating costs, but generally speaking, it's considered a bit more expensive than TEG. And then there's another level down beneath that, which gets into sub 5 ppm, less than 1 ppm.
Right.
And not all gas streams need that level of dehydration to start with. So it's not just a which gas, which technology. There's a lot of questions and complexities that kind of die back into it. And along with that is it depends on other pieces of the puzzle. So I mentioned that TEG is a hygroscopic material. Well, it also has carryover aspects. So the downside of TEG is that it's really difficult to keep all TEG in your process and not going with the gas. Is it a big deal? It depends. So if you go into a gas stream for 20, 50 years and you have TEG residue that's going in there and a little bit over a long time means that you've got a lot of hygroscopic materials in there. Well, now it's also taking in moisture of the gas, the residual. Right. So if you're 50 ppm going to the pipeline and you have TEG in your pipeline, you're basically forming these pockets of really high moisture, and you're kind of perpetuating that in not in a broad homogeneous sense, but in a very acute local area of low spots in the pipeline. And then, just on a cost basis, if you need less than 1 ppm, then use a technology that's suited for it. If you don't need less than 1 ppm, it's not really the best technology out there because you're going to have trade-offs on cost as well.
You can see why I like to hang out with Spencer. I'm just hoping that at some point this intelligence will,
Spencer, what do you want from McDonald's?
Is it
Well,
osmosis?
well, let's see.
2 cheeseburgers, ketchup only.
Well, it depends.
Well, it depends.
Where are we going? Where are we going after this?
Not on that one.
But at the end of the day, it's cost for our customers, and it's which technology do you use? Why don't you just say if you need water out, water's bad, let's just get to the tightest water we can get out, which would be molecular sieve. Well, there's cost. So glycol or TEG has the lowest cost, but it removes the least amount of water.
Right.
BSF Zorbede gets you that lower threshold below 50 and is more expensive than TEG. And then the most expensive is molecular sieve. So what's good enough? That's the question for our customers, because they want to do it at the best cost, at the lowest cost and still meet the specifications. So for our customers, it's always about meeting the standards, meeting the specs, accomplishing the objective, but doing it at the least amount of cost, with the least amount of cost.
So how are we maximizing, or how are we reducing it, I guess, the most? What are
What's
we
our
doing to
approach for
reduce
cost management?
So what we've done at NOV is we've looked at how does the technology work for temperature swing absorption beds? They use more energy. Traditionally speaking, the way that they work is you have 2 beds, right? You have a bed A and a bed B, and a bed A is drying the gas, right? The CO2 or methane stream is coming in. It's pulling out the water from the gas, and then once over a period of time that bed is full, you cycle over to regeneration. So now this will be an absorption, and through heat, it'll regenerate the beads so that it can do it again.
Oh, nice.
And right now they're timer based, and the time is based on the hottest day of the year when there's the most moisture in that gas stream.
Right.
So you're gonna cycle an absorption for a specific amount of time based on the worst case conditions.
Yeah.
And when you're operating at any other time of the year, you're going to be operating at less than optimally. So you're gonna absorb maybe half of that bed,
Yeah.
and then you're going to prematurely go over to regeneration.
Mm-hmm.
And the bed life. So these beads don't last forever. Every depending on if it's emulsive or if it's sorbed, you're going to have to change out that bed every several years. For sorbed, it's roughly 5 years. For emulsive, it's 2 years or so.
Right.
And so that bed life is dictated and impacted by the regeneration cycles, those heat cycles.
Yeah.
So if you increase the number of cycles in that bed life, you're going to cut short that bed life.
For sure. Yeah.
And so if you're operating on a timer-based system, you're losing out, and you're not gaining the optimal amount of absorption time and cycles between regeneration. So what we've done, as opposed to a timer-based system, we have what we call our smart bed adaptive control design.
Okay.
And what the smart bed does is it says, okay, we're going to measure the moisture content of the gas coming in.
I was about to say, put some sensors on that thing.
That's right.
Let's go. That's right.
So we measure the moisture content coming in, and then we adaptively control the absorption time based on the conditions of the moisture content of the gas.
Condition-based monitoring.
Exactly.
Instead of on a time schedule.
So if you can prolong that absorption cycle,
sure.
you're reducing the number of cycles in the life of the bed, and you're increasing the bed life. You're also using energy more optimally, so you're cutting down on energy costs and operation costs. So,
right.
yeah.
I think that's kind of maybe what I was getting at the very beginning of, like, what do we as NOV bring to this technology that has been around for a while? And to me, it's like, yeah, we can bring scalability, we can bring cost reduction, because that's what I've heard from other people in different areas of, let's say, alternative energies, of like, that's what we can bring, is how can you cut the costs in half, or fill in the space of whatever the solution is.
20 to 50%.
Yeah, we seem to be able to be in such a great position to do that for these different applications.
No, and it's a good way to put it is that, if you know you can do it, why not do it?
Right.
And that kind of brings up the question is like, why aren't people doing this already?
Right.
And that kind of goes back to that education is almost 90% of it, 10% of the innovation is, yes, it's sensors. We most of the time already have the sensors there, but it's being able to use that knowledge in a smart, intelligent way, and to make it to the point where it's, the confidence is built up where people just want to do it. Kind of an interesting point is it's the same thing as far as if you have a pool and you're cleaning your pool, you have your pool system running all the time to keep your pool clean. Well, interesting fact is about 2 gigawatts of power in Texas is used to keep pools running. That's almost 20% of Houston's power consumption just on pools that run. Well, you only need a Holland for 25, 30% of the time.
Right.
So the simple question is, why don't people just run their pool filters less of the time? Because they're used to it running 24 hours a day. They're concerned about it. So all these things kind of factor in is that if you look at what we're doing for smart bed deployment, most of it's just convincing and having the conversations on the technology is there, the confidence is there, building up to it. The practicality side is you look at it as far as what's coming in, you look at it as far as what's going out, basic sensors, the availability is already there, the information's already there. Now how do we apply that to do smart switching or the smart bed advanced controls? And what it's doing is it's taking that, that design point of the hottest hour of the year, or forecasted hottest hour of the year, and anything beneath that is basically wasted energy that's being used on the regeneration cycles.
Yeah.
So the main power on these dehydration systems is there's a little bit from the electrical control standpoint, very, very small, but the majority of the power is actually on the regeneration heat. Whether that's coming from a steam plant or it's coming from electrical heat, but that power duty is being used every single time there's a switch that takes place, whether it's every 8 hours, or in some cases, if you can extend it down to 40 or 50 or 60 hours between the regeneration cycles, that just means it's less energy consumed, and it's also less emissions going out the door for essentially an underutilized system that's being regenerated there as well. Yeah. Kind of the differences is if you look at it, a chart would show, or the chart shows that you're basically looking at a very variable output with respect to the cycle times or the loading of those beds. And on a timer basis, it's very consistent from a time standpoint. Every 8 hours, every 12 hours, whatever the design point is. but it means that the loading could be as low as 20% when that switch takes place, or possibly at best 80, 85, 90%. But never is it actually near that 100% level. When you switch to the smart bed configuration, what it's doing is it's very variable in cycle times, but it's almost reaching that 95, 98%, whatever your threshold is on your input and the output as far as a confirmation goes. So you're really trying to maximize the bed capacity. And this desiccant, or as it is the Zorbete, or the material, the media that's in the beds, they can take more. So every single time there's a switch that takes place, it never actually reaches the full 8 hours at that hottest hour of the year.
Yeah.
Right.
You have sun up, you have sun down, you have rain, you have clouds. All those things factor into variability on what that input may be on the gas stream.
And I think we have even a graph, right, that kind of shows all those changes, those ups and downs, and then with smart bed, it's just like solid.
Exactly. It's showing kind of a within one day or within a few days, and then it's showing over the course of the year. And you can see it's highly variable in one, and it's very, very level on the other. And that's just basically with smart bed off, very variable as far as the loading. With smart bed on, it's very consistent, and essentially it's extending the bed time and absorption to reduce the number of cycles on the regeneration.
And is that with CO2, or does that kind of technology apply to other gases that we were mentioning?
It does apply to other gases. So CO2, in the case of ambient atmospheric conditions, much of the upstream in that CO2 case is actually from an upstream compression. So the compressors have intercoolers. The intercoolers can be air cooled, or they can be water cooled, but those all tie back into cooling water systems or air coolers, which are directly back to the environmental aspects of temperatures. When you get into natural gas, there's some interesting things that come there. It's the same premise of it, but there are some configurations needed. So typically a plant would have a cooling water system, and it's the whole plant cooling water system. And there's some benefits that can be done by taking off a portion from an air cooler perspective rather than an entire plant, but actually take it off as its own. Because it comes back down to is if you're trying to reduce the energy, and you're using, say, an electrical or electric heat exchanger, the power or the cost of that BTU or heat input, as it is on electric heat exchangers, is very expensive. An air cooler is very inexpensive. So you can basically increase your duty or your runtime on a cooling system, which is at low cost, versus the cost on a heating system, which is high cost.
Yeah.
So it's kind of like if a penny per BTU on the cooling water system, absolutely run that for 24 hours a day, versus say $1.50 a BTU on your heating system, and you only run it for 8 hours a day. Well, 8 times 150 penny times 24, the math starts working out very simply there. So in that case, it's somewhat education, but it's also somewhat configuration of how the system and the plan is being set up there as well. And then the other gas is hydrogen. A little bit different on that one, because typically we're talking about green hydrogen, where electrolyzers are being used, and it's green power from wind or solar or from other low carbon power sources. On the wind and on the solar side, it's more on the flow rate of gas, meaning that when your electrolyzers are on, if the sun is shining solid at the middle of the day, then you have a very high power, which means your electrolyzers are putting out more gas flow. If you have, say, a cloud front that comes through and you have a 40-50% reduction in your power output, your gas volumes are also lowered by a flow rate there as well. Nighttime, different times of the azimuth as far as the
It's dependent on what it's being fed.
Exactly. So it's a little different where in CO2 and also in methane or natural gas, it's more on the moisture loading in the gas.
Okay.
In green hydrogen, it's more on the gas flow. It's typically very consistent loading, but it's very much variable on the gas flow.
Let's all take a breath.
So,
wow.
It depends.
This is so complex.
Well, that's kind of what I was going to ask. Now we're at this point. Can y'all give me like a summary? So we've covered a lot of different elements of it leading up to what smart bed is. Can you give a summary? Where's the value for that NOV is adding simply for the customers?
Yeah, so what does this mean for our customers?
Right.
Why would they want a smart bed solution as opposed to timer based? So essentially what this means is what the smart bed solution is going to do. It's going to increase your bed life. So that means instead of 5 years between swapping out the beds, and you got to remember, they got to go out there, they got to drain the complete the beds, they got to add new beds, new media. So it's going to extend that time between, which plant shutdowns and other, when you're operating in a plant, really can help with scheduling and maintenance costs. The other thing is it's going to also cut down on your energy. So the initiative here is to try to save energy, right? Clean, low carbon energy. So we're going to save on energy, which is going to essentially reduce emissions. So save energy, save on operating costs, extend your bed life, reduce emissions. That's what we're doing for our customers.
It's oddly similar to me. The themes, like your customers worried about costs. It sounds the same as like operators in a drilling space, or they can plan better from technology helping them for operations being more consistent. I think about Novos on a drilling thing. The whole thing is it's supposed to make drilling more consistent. Well, you might be able to drill faster at some points with a real actual driller, but can they do it over a prolonged period of time? And how does that help the like it seems like we're solving the same problems in a completely different realm, and we're really set up for that.
Yeah, and I would say it's a weird one, or it's an interesting one in the sense that most of the time when you're trying to get energy savings, you have to deploy capital.
Yeah.
It costs you more, you get lower operating costs. In this case, you're already paying for the hardware to do the work, but you're taking advantage of the inefficiencies that are built into it inherently by the traditional timer base.
Okay.
So you're it's this one scenario is like, we can save you money. How much does it cost? Nothing. You're nothing. You already have the equipment. You already have the controls. We're just trying to educate people on how best to use it. And in some cases, there's some additional sensors, but you're talking very small increases of 1%, 5% in capital cost to have a full spectrum of full visibility, future prognosis of lifetimes. Those other aspects come along with it. But fundamentally is the hard equipment that's doing the work on the gas, it's already there.
And this is why you said it's 90% education.
Exactly. Exactly.
Yeah.
And when you're selecting the technology, right, it's this ambivalence or hesitance or reluctance to go away from the technology that's well-known and is cheap, to go to a technology that actually provides confidence that you're not going to have these corrosion problems downstream without the major cost increase. So that's what.
Yeah, it's like I have a sprinkler system that's on just a timer base, and I'm scared to turn it off because I'm like, well, what if I forget to water my lawn? Or what
why
if something
can't it
goes
just know
wrong?
when the rain is going to fall?
Exactly. Yeah. Like what if?
But they have those.
I knew it. Here we go.
There are sprinkler systems that will actually monitor the weather. They're connected to the internet. They'll pull in what the forecasts are. And
Tell you what,
only turn on when needed as well.
if I'm ever going on a trivia, going to a local bar for trivia night, I know who I'm taking with me.
Just not names.
Okay.
Not names.
I'll work on
Brent
the
knows
names.
this very well.
Yeah, I'm not gonna
You know the global usage of pool systems. So
Wouldn't it be great if there's airport TSA related questions? We must be talking about Molson
TSA?
and all this other stuff.
yeah,
Temperature swing absorption. Yeah.
I got stopped by
Different
them
TSA.
yesterday in Cincinnati.
Oh man. Well, thank y'all both.
Yeah,
for
this
coming on.
was
This is a complex topic, but
an
I think
education.
y'all are able to communicate it really well, and it's very interesting.
I think it's obvious y'all have spent the time, like you said,
Yeah.
to educate yourselves and seeing the value there in the wait. You've got the components, Mr. or Mrs. Customer. Let us, we've worked out the kinks on how to best utilize what you've got. I think that's incredible.
Yeah.
So
You've made me understand it, so I feel like if I could follow this conversation,
Right,
anyone can.
right.
Hopefully.
We appreciate you guys. Thank you for having us.
no, yeah, thanks for being here.
Very much.
Thanks much.